Okay, students, we're going to do, I want to discuss exam 2 for a minute. It's on Wednesday. It'll be here in lecture. It'll be similar to exam 1. So what we're going to be doing, and we'll have one written problem, all right, that you'll turn in. You'll turn in everything, okay, and you have one written problem. So instead of clicking, you'll have Scantron, and you'll turn that in, and then you'll have your test paper with the written problem on the last page. Okay, you'll turn that in, we'll grade, and I'll grade it. Right, and then that'll be, and so you'll turn in your test as before, along with your Scantron. All right, so that's my decision on that. The fair game. Actually, can you switch over to computer? Get me chapter 22.4. Okay, 22.4, we're not really going to talk too much about it. We're going to talk about this right-hand rule. Basically, go ahead down a little bit. I put this diagram in. I don't know if you guys figured it out. Figure A1, that's me. I borrowed it from I borrowed it, five-finger discount from another website, and it's now inside our textbook as figure A1. In other words, addendum number 1 from Dr. B. And we're going to be talking about this down here below, QV. Can you move it up a little bit? Q equals VB sine theta. Now they have a very terrible description of it, but I'm going to try to walk you through it. And then go back up to the diagram. This diagram is pretty good. All right. We're also going to have, go ahead and switch back out. We're going to have some demonstrations today up front. We were just fooling around with it. Primarily this one that you see up top, but I'm going to be putting it on the camera. All right. And we're probably going to have participation from somebody in the audience. You won't be on the recording or anything, but you'll be helping out up front as a volunteer from the audience. And then we'll do some calculations on the document cam. So your homework is basically to prepare for exam 2 up to about this point here. And this is 22.4. We're going to talk about that today and just do a few simple things with that. That's the force on a moving charge. And you know, the interesting thing, a current is the source of the magnetic field. And the magnetic field that you produce in from one current produces a magnetic field, and that magnetic field can have a force on another moving charge away from your source current. All right, and so if you have a current over here on this side of the room and an electron on that side of the room, the current's going to create a force if the electron is moving. So it's really current to current, and that's why the ampere is considered a fundamental unit in the metric system, not the coulomb. But we'll get to that in a few minutes, and we'll do that on document camera. Now, let's get some clicking going. We're going to do a little bit from the readings and a little bit from session 20, and actually a little bit of review to start. So now last week we talked about the capacitor with a resistance, and this is a capacitor connected to a resistance and a battery, a voltage V. Right now, the loop equation for this, the Kirchhoff's law equation, is V equals IR. IR being the voltage drop by Ohm's law, which we talked about 2 weeks ago, at the resistor, and then 1 over CQ, that's the voltage drop in the capacitor if it's charged up with charge Q. Now this thing is going to build up charge on the positive plate, pushes it through the resistor, so it does a little work there. And as you know, as I mentioned, this particular situation is the charge up situation. All right, so this is where we have the saturation curve that we talked about Friday, and which you can see in the textbook. Now, the process that we're going to talk about now is take the battery out and let the capacitor discharge plate back. So the charge is, the conventional charge is now going to go counterclockwise in this diagram. Let's see, did I have the other one? No, I don't have this one. This one is going to charge up clockwise from the positive plate over to the battery over to the positive plate of the capacitor. All right, and then electrons are going to scamper the opposite direction from the negative plate of the battery to the negative plate of the capacitor. I mean, that's physically what's happening. But I don't have the direction of the current. But in this one, the current in charge up is clockwise. Here it's counterclockwise. All right, so we take the battery out and reconnect, and then discharge the capacitor. Now this is where the resistor is going to, maybe if it's a light bulb, it might light up, or it might get warm, or it might shock your heart back into a sinus rhythm if it's fibrillating, because that's what defibrillators do. Right there, that's it. They drop a little bit of current, a little bit of voltage across your heart muscle, try to get it calmed down from fibrillating. And you know, atrial fibrillation is one thing, but ventricular fibrillation, that's death. So you got to have that. That's got to be, that's sudden cardiac death is what they call that. So this thing's got to work, defibrillators. All right. Now, let's talk about the kind of loop equations that represent these processes. All right. And you actually, this should be easy. Here's your first clicker question. And hold on. I don't want this multiple choice. I want it. Hit refresh. I'm going to make everything short answer today, even though this is just A and B. Okay, hit refresh and then choose A or B. Can you guys do a count, please? 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. Uh-oh, we got some explaining to do. It's not a clear A or B, and actually this is the correct answer, A. And the reason for that is simply that this is the battery out. There's no voltage on that, you know. So on the discharge loop, there's no, you know, there's nothing on the voltage source for a voltage source. So the only potential drops you have are the drop on the resistor R, and then the voltage drop at the capacitor, 1 over C times Q. So, all right. Now, I'm leading you towards something from chapter 23. I'm going to give you a sneak preview of some stuff at the end of chapter 23. And to do that, I'm going to ask you this question. It's a review question, but it's a good one. All right, so there's the discharge formula, the loop formula for the discharging circuit. And basically what that means, whatever the capacitor loses gets worked at the resistance in the form of energy dissipated. And the charges don't disappear, though. They simply equilibrate. The capacitor goes back to being neutral. You know, I shouldn't have said that, because that would make a great exam question. And by the way, I haven't written the exam. I'll be writing it right after this class today. So get your questions in now and form my mind. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Uh-oh. We got a little bit of, it's good that we're reviewing this. Correct answer here is A, the current. And let me go back over here. The current, yeah, current is defined as delta Q over delta T. Right, that's the definition. R is a constant in an ohmic circuit. Most of the time, you consider it a constant. If something gets really, really, really hot, if it's doing a lot of I squared R heat and it hasn't melted yet, but before it melts and fuses, you might get a change in the resistance might go way up or way down, and then even more I goes through. If the resistance goes down, the I goes up, and you get even more I squared R heating, and you get hotter and hotter until you break it. Stuff can melt. You can fry stuff. And of course, Q is not delta Q over delta T. Capacitor is a constant. And just as a reminder, here's the exact formula for discharge. We talked about this last time. The time constant tau, we didn't really talk about it too much, but we will have reason to talk about time constants and actually frequencies in chapter 23. And I'm trotting you through this stuff to give you just a little flavor of chapter 23 for after exam 2. All right. So these are exponential. So whenever you have a quantity, the time evolution equation, delta Q over delta T being proportional to the charge Q or to the whatever the function is, think exponentials. In this case, it's discharge, so it's a decaying exponential. That means it's minus T over something or minus, T times something, alpha. That's what we were working with last week. Now, let's do a couple questions about magnetic field. And this is going to fry many brains. So I'll give you a little bit of time with it. All right, Jared? I don't want to, I mean, I do enjoy seeing your guys' brains fry, but I don't want to cause too much. So let's get to it. All right, here we are, a conventional current. Comes out of the plane of the display, so out of the wall. So it's kind of coppery colored, and the out of symbol toward you from the plane of the display is a circle with a dot in the middle of it. All right. So it's parallel to the z-axis, which is not shown. The x and y axes are shown. All right. Now there's a magnetic field at point G. What direction is it? Go ahead and type in an answer and hit the send key. Don't forget to hit your send key because you're on alphanumeric. Yeah. See, so you got to go like. Don't dislocate your arm though. And use the right hand rule. Brandon Dishman. Right hand. Right. Not this one. This is the alternate right hand. The other right hand. No, don't use that. Use this one. Yeah. Use this one. All right. The true right hand. The reason I say that is because students on these magnetism tests, a lot of times I'll see them doing right hand rule, but using their left hand. And I've done the same thing. So I'm just kidding around with you. So. And I see everybody trying to make a decision. And why don't you make a nice big sketch, because we're going to do a few other points. You may as well make it part of your notes. One minute. Good. See this, Kendra? See all the students going like this and stuff? You know, they're all over the room. That means they're thinking. That's exactly what we want. And they're talking to each other and they're gesticulating and stuff. Oh my goodness, this is my wife's power. How did I get? I must have left mine at home. Is there another power cable in there? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. What's your count? All right, I know at least one student without a clicker. Okay. All right. Now, my wonderful students, you guys always cheer me up, almost all the time. You know, I came into school today really cranky because I had to walk halfway across campus to park from my car because I couldn't find a spot. I'm sure that's never happened to anybody in here. But anyways, I was mad as a hornet when I got here. But you guys have cheered me up, so that's good. Um, yeah, now look at this. We got a lot. We got some of each. You know, we got all the flavors of the rainbow, as they say. So, well, not all of them. A, B, C, D, and E. Wait a minute. Maybe we do have all the flavors. F, G. Yeah, we got all the flavors here. Everybody's all right. So you know what this? First of all, what this tells me is there's a lot of flailing. You guys got caught napping on this. All right. Now, what you want to remember is actually A is correct, and let's see. That is not the biggest group. Now, let's take a look at what we got. All right. Now, I'm going to hobble over to this display over here, and I'll just do it in front of this display. So could you clear a space for me? Here we go. All right. All right. So what you want to think about is the right-hand rule. Now, I remember in grad school working on a magnetic field problem to study for a big important exam, and it was during the summer, a qualifying exam. And I was working on this problem, and I kept getting it exactly wrong. You know, I was getting a minus sign instead of a plus sign. I said, what the? And then I realized I was doing right-hand rule. I was writing with my right hand and calculating on my calculator with my right. But I was doing right-hand rule with this. And one of my office mates pointed it out to me, and I went. So, and I've seen you guys. Well, I haven't seen you guys yet. But many times, students doing magnetism exams, I'll see them doing this, and it's the only time I will ever help you substantively on a test. And I'll simply say, use the right hand, not. All right, so let's do it. Right hand. The current is coming out of the plane of the display. So you put your thumb in the direction of the current. And then the fingers of your hand symbolize or encode the direction of the field lines. So the field lines are going to be going anti-clockwise for this current. And therefore up here, they're going north. All right? So remember that. All right? Glad you're comfortable. I wish I could do that. Okay, so make a note. The correct answer here is north. And I was going to allow for a few moments of sketching here on the document cam, but I think it's better that I walked over and showed it to you in person on the screen. All right, you ready for another question? All right. Get my cursor. All right, point S. You guys can circulate. Ten seconds, starting now. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, you ready to look at the answer? Did anybody get this? Very good. And I could see that 97% of you got this. All right, good. Let's try another one then. How about point P? Keep circulating. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see. Point P up in the northwest. So the answer should be B, right? No? Huh, good. I didn't trick you guys. Southwest. Yeah. So so go ahead and if you've got a diagram in your notes, add a little southwest vector. Now we don't have any magnitudes. We're not going to be doing that until next week, probably. Figuring out the magnitude of the field around a circuit with a current, with 1 amp or whatever. But at least you can draw in an arrow to the southwest. All right. Now that you guys are geniuses, let's see if I can melt your brains. See, I've been saving this one up. Do not let me catch you napping. Conventional current into the plane of the display. Dun 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 dun. Dun 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 dun. Don't hurt your shoulder. Eduardo, just stand up at the diagram and show them. Stand up at the screen and show them. Just show them. If they don't believe you, just show them. Yeah, the z-axis is coming this way. So anti-parallel to that is the opposite direction. No, I'm talking about the current. The current is the positive z-axis is this way. So the negative z-axis is this way, and that's the direction the current's going. So we will call that anti-parallel to the z-axis. Okay. Just means into the plane of the display for this. Okay. So, use the right-hand rule for that particular direction of the current. And then make your decisions. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2. See, I already burned somebody's brains over here. They're crying. You're not crying? Just sinuses? Okay. All right. I thought he was crying over here. All right. Oh my goodness gracious. The answer is okay. And you guys did not get burned. 95% of you, anyways. So if I put a lot of these on exam 2, no, you already said it. Nope, too late. You already said it. Too late. No, you want them, you got them. No, too late. I saw a student back here on the other side of the room. Yeah. And then everybody said, "Oh, wait a minute, what did I say?" All right. Um, all right, I'm going to pause the recording here, and we're going to do some demonstrations up here at the front table. And so go ahead and sketch that. And I'm going to get my sketching implements here. We're going to do some more sketching. And that is known as the jumping wire demonstration. Go ahead and make a note of that. The jumping wire demonstration. And the first one was just magnetic field and a current carrying wire. There's no fancy name for it. Well, this one's known as the jumping wire. All right, now let me get some fresh papyrus here. All right, here we go. Clear this stuff out of here. Can you guys message those to me in web courses, please? Your two images.
Picture this one too?
Huh?
Did you want to picture this one too?
Sure, go ahead and do that. And actually, I think I'll come around there. Take one too. Instagram. Oh,
I told you, didn't I tell you about switching to art?
okay. Joy, Joy, could you wheel that chair next to you over here for me? Thank you. All right. Okay. Let's let's continue with our discussion. Um, as I mentioned in chapter 23, I believe. Can you call up 23.9? Go ahead, page down a little bit. There we go. Keep going down. Keep going down. Keep going down. There we go. Stop at that circuit diagram. Now this is what we're going to be attacking probably next week. This is a capacitor and a resistance and a voltage source. And up there, that curly Q. Okay, switch out of there. That is this. All right, that's what this is. And it's a symbol for a coil or some kind of electromagnetic electromagnet. All right. And so that's kind of what is ahead for us. And I'm going to talk about that for just a minute. And then we're going to do some calculations of the magnetic field. So let me kind of get over here, and can you switch over to the, all right, can you switch to the document cam page on the podcast, on the YouTube? Good. All right. So What's today? The 14th? Okay. Um, let's let me do a schematic diagram like this. This is the way I usually draw any kind of an electromagnetic device. Now, if the current's going in this direction, the positive current, and let's say that the positive current is a function of time, I of t, then the magnetic field lines inside concentrate as I of t increases. All right, now I'm not going to draw in the field lines. Actually, I will. Let me draw an end-on view. Okay. Now this is going to, I'm going to kind of draw it like a, all right. So here's my, I'm looking down the pipe. This is looking into, I'll call it point A. So here's point A in the circuit, okay? Now if the current is going this way, let's say that the current is going counterclockwise through the coil so you are here, okay, and you're looking at point A, and here's that view, okay. Now when the current's going, and I'll put my pencil here in the direction of the current. All right, at that point, my current's going kind of northeast a little bit. All right, tangent to the circle. So now my thumb is in the direction of the current. All right, and my fingertips are curling up towards the camera. They're getting blurred. Okay, so that means that the magnetic field inside is coming out. So put a B symbol as a vector B symbol there to represent inside the coil the current's coming out toward you. Okay. Now here's what those. All right. So it's coming out towards you, towards this direction. And if you look at this carefully, see that? A pencil with a dart. This symbol, a circle with a dot, is meant to represent the tip of an arrow coming toward you. And so that's the international symbol for up out of the plane of the paper, up out of the plane of the display, whatever you're looking at, out of the plane. Into the plane, the opposite direction is symbolized with an X. And the X represents the feathers of the arrow. At the end of the arrow, so it usually has some fletches, some feathers, to guide it along its way. So those arrows, they symbolize that the arrow's going away from you, the part that's going away from you. So this one, the arrow's coming towards you. You can see the tip of the arrow, and then you duck, and then when the arrow's flying away from you, you see the feathers of the arrow leaving, moving away from you. Okay, so when the field lines concentrate, the B is stronger. And so this is comment number 1. And comment number 2, as I of t, let's say that it gets weaker. The vector B, the magnetic field, gets weaker. Still going in the same direction, but it's just a big current, a lot of magnetic field. All right. Now that's the same if it's got an iron core or if it's got an air core. So any kind of a coil, this is going to be true. All right. Now let's do another circuit device that has varying field strength. What's the other kind of circuit device that we have that has a varying field strength or can have a various different levels of field strength? Think. What other circuit devices do we have? Raise your hand. You can have an electric field strength, but it depends on the. Yeah, Andrew. Capacitor. Yeah. All right. So let's draw a capacitor for number 3. All right, so capacitor, parallel plate capacitor, and I'll just draw one field line, positive to negative, and we've got a current coming in here. All right. And so we have an electric field here. And this one, 3, E gets stronger as what gets bigger. What property of the capacitor means that the electric field is going to be stronger? See, good question, good test question. What is it about a capacitor that will increase or decrease the strength of the electric field? Huh? The voltage is not part of the capacitor, though. What is part of the capacitor? Not the current. The charge load. So as Q of T increases, okay, so as your charge, and we've talked about that. Comment number 4, E gets weaker as Q of T gets weaker. So as those electrons boogie out, they bug out of the capacitor back to the battery or back through the resistance to the other plate. They're going to get the electric field is going to get weaker and weaker in the capacitor until the electric field's 0, and then you don't have anything left stored as energy. Oh, did I say energy? Yes. This is energy. Oh, okay. So here's let me zap out here a little bit. All right. So this is energy here in the electric field, and it's actually the square of the electric field, which everybody that knows Maxwell's equations should know that the electric field density is proportional to the square of the electric field. Right, Andrew? Yeah, he's on Facebook over here. I told him he could do homework in here, but I never heard of a professor giving homework in Facebook. All right, so there's energy in the magnetic field. Do you know of another physical system that has 2 forms of energy? Oh, wait a minute. Wait a minute. Something's a little bit. We forgot something here. The current is greatest Q of T is greatest, but what's the relation between current and Q of T, the charge load? How are they related? What's that? What's I of T? What's the definition of I of T? No, current is a function of time. That's right. Current past a point. But in terms of Q, how do we define it with Q? Using Q. Delta Q over delta T. So this is a delta Q over delta T up here, and this is a Q. All right. So two forms of energy. One with I'll call it U of T, some unknown, and then delta U over delta T. Some unknown, the time rate of change. Anybody think about that? I'll let you think about that for the next day or two. Sure. So there's my unknown. So I'm just saying there's some unknown that I know that you guys also know it, but you don't know you know it. That the function and its time rate of change both carry energy, or there's energy dependence on both of these. And there's a physical system that you've studied in Physics 1 that has this property, just like this property, the E and the B, right? The B is related to the current, and the E is related to the charge, all right? And they both store energy. All right, I'll let you think about that. Can you switch to the next document page? Okay, now let's do magnetic force. See how this looks? It looks black. It doesn't look red. I'm using red ink here, you guys. Okay, so a moving charge, all right? Let's think about a moving charge. All right, so let's draw a proton. And let's say it's moving in this direction. So there's its velocity. So that could be, like 20 meters per second, or 2 times 10 to the 8 meters per second, which is 2/3 of the speed of light, or any other velocity. All right, now I'm going to draw in the top 4 or 5, 6 lines of my notebook paper. I'm going to draw a set of X's to represent magnetic field into the paper. And I'm going to try to make them equally spaced. Now, if you have graph paper, you can do this really precisely. All right. And so this is going to represent a uniform magnetic field because the field lines are equally spaced. All right, let me go across here. Equal densities, and except where the proton is. All right, so this is like between the poles of a horseshoe. That's why they have horseshoe magnets, to make the magnetic field fairly uniform in between the two poles, between the N and the S of the magnetic field. All right, so there's my, and we'll just consider that to be dot, dot, dot to the left and right, dot, dot, dot to the to above and below, okay? So this is just a miniature sketch. All right. So X represents magnetic field into the paper, right? All right. Now, the force on this charge is a right-hand rule. Okay, so there's a right-hand rule force on the proton. And the rule is like this. You put, let's see, V cross B. Okay. So you put your fingers in the direction of V. You curl your fingers toward the direction of B. So for me, that's like this. And then your thumb points in the direction of the force. All right. Now this, can you find the right-hand rule for that? It's in 22.4, I believe. All right, there's a diagram. All right, so that means that the force is upward. All right. All right. So V, B, and then is that an electron? Okay. Is that the top of that's the top of the hand that you can see, right? Okay. All right. So now you can let me point out what section is this? Okay. So chapter 22.4. All right. Now the magnitude of it is something called a cross product. All right. Now here's the fancy vector version of that. The force on a moving charge is equal to the charge Q times something called a cross product. And that's V cross B. All right. Now, V cross B is where the right-hand rule is. Okay. V, fingers in the direction of V. Curl towards B, thumb is the force. All right. Okay. Fingers along V, curl them to B, which you can only do in one direction. If this thing, the magnetic field is into the page, so I can only curl my fingers like this. So my hand is parallel to V. I curl them to where B is down below the page, and then my thumb is up in the direction. So that gives you the direction of the force, and it's a pain in the neck, but it does give us some information. All right. So yeah, I know there's different versions of the right-hand rule, so it's a pain in the buttocks. Yeah, you do it like I do. Yeah, yeah. I've made a comment. Are my comments visible there? Yeah. I severely hate. Yeah, there's a the diagram. Go ahead and switch to document to the computer. All right, now in our textbook, I want you to at least read this far in the textbook. All right, and it says, I severely hate this version of the right-hand rule. But it may make sense to you. So you go ahead and look at it. And I showed you my version, and they have their version, which I consider to be almost Martian in strangeness, but, you know, there's a lot of You know, whatever works for you. So this is the Dr. B version. Okay, switch back to the .cam. All right. Now we're going to make a calculation. Can you switch to the next page of document cam? All right. So we're going to do a calculation, and let me go to the next page for that. And what we're going to do is we're going to have an electron, all right, and the speed of the electron is going to be 2 times 10 to the 8 meters per second. Now that's 2/3 of the speed of light. And we see electrons at this speed all the time. It is very easy to get them up to that speed. They're called relativistic electrons, and we're able to get those things accelerate. Protons a little bit harder. But you know, the sun produces electrons and protons in the solar wind. Not quite this fast, but pretty fast. Anyway, so this is 2/3 of the speed of light. All right, so this is a realistic example, and it's an electron. All right. Now we're going to say that the force on the electron is equal to 2 times 10 to the minus 6 newtons. All right. Now that doesn't seem like a lot of newtons, but for an electron, that's going to be a mighty, ginormous number of newtons. All right. So let's figure out B. All right. And what we're going to do is we're going to have, and here's the diagram. The electron, here's an electron zapping through, and let's just say it's going to the right. All right. And the magnetic field is into the paper, so I'll just put an X here for the magnet. I'll just put 1X. All right. So it's understood that the magnetic field is in this small area where the electron is uniform. All right. So now, so here's the velocity of the electron. Now, this is an electron. All right. So V cross B is up, but it's an electron. So the force is the opposite of that, right? So the force is going to be downward. Okay, and it's because, and let me just write it down here. I have minus E for the charge, and then I have V cross B for the vector part. And we're going to plug in some numbers here in a minute, but V cross B is still up. This thing is up. But this minus sign out in front from the negative sign means that the actual force is the opposite of what a proton would do. You know, the one we just did was a proton, all right? Force was up the paper in this direction. But now we got an electron. Electrons do the opposite, all right? And here's another way to think about it. The conventional current here is going to the left. Electrons going to the right, conventional current to the left. All right. Now let's do some plugins here. And we're going to get a unit for the magnetic field. All right, so here we go. And I don't know how this is going to work out. I just made these numbers up on the fly. Hopefully it won't blow up in my face. All right, so I have 2 times 10 to the minus 6 newtons equals minus 1.602 times 10 to the minus 19 coulombs times 2 times 10 to the 8. Well, it's going to be pretty small. No, this might be all right. 10 to the 8 meters per second times the magnitude of, and everything is perpendicular. So in the textbook, they mention the sine of the angle between V and B. So V and B, I'll make a note, V is perpendicular to B. All right. And so that means the force. So there's no trig to work out here. We don't have to have but if there is an angle, and we're not going to have that on the exam. We're not going to have any sines on the, but if there were, you just calculate sine of theta in there, and then you do the same thing. All right, so let's calculate this. All right, so this is 2 times 10 to the minus 6 newtons equals, all right, negative 3.204 times 10 to the minus 11 Coulomb meter per second times B, whatever B is. Okay, anybody disagree with that? All right. Now I've got a minus 6 over here, and I've got a minus 11 over here. So I'm going to get 10 to the positive 5. So this is going to be a pretty strong magnetic field. It's really strong. But notice over here, I have coulombs and per seconds. Now the per second comes in from the velocity, but we also know coulomb per second is the same as an amp. All right, so let's modify this. 2 times 10 to the minus 6 newtons equals negative 3.204 times 10 to the minus 11 ampere meter, and then times B. All right. Now let's do some scientific notation. And we'll clear the right side by doing some calculation. Can you swap me to my next slide? Okay. So now let's do that. So let me skip down a little bit. 2 times 10 to the minus 6 newtons, and then and I'll put a minus sign up here now. 3.204 times 10 to the minus 11 ampere meters. Whoa. That's the size of the magnetic field. Let me take the vectorness out of that. Let's just do a mag. So drop the minus sign now. We've got the directions figured out. And we'll just do magnitudes. The minus sign has done its work. Now we're just going to get the magnitude. And hey, you guys, what are the units of the electric field? Remember? What per what? Electric field, newtons per what? Newtons per coulomb. This is newtons per amp. And it's also got a meter there. So this is like weird. But it has a newton per coulomb in there because newton per amp is newton per coulomb per second. So we're doing all right here. It's not too bodacious. So let's do this calculation. What's 2 times 10 to the minus 6? What's 2 divided by 3.204? It's about 0.7, 0.6 something. All right, I'll be forced to do it myself. All right. 2, enter exponent, negative 6 divided by 3.204, enter exponent, negative 11 equals. What on earth? All right, let me switch this to scientific. .24 times 10 to the 4. Anybody get? Okay, 6.24 So only 62,000 Teslas. That's not too bad. So this unit, Newton per ampere meter here for the magnetic field. That's known as a Tesla, which is named after Nikola Tesla, not the automobile company. The automobile company was named after him. So the symbol for Tesla is capital T. All right, and you can read about this in chapter 22.4. I also have that highlighted. The Gauss is the other metric unit, and it is equal to 10 to the minus 4 Tesla. And that's in a whole different system of units, but it's considered a metric unit. And the Earth's magnetic field is about half of a Gauss. So a 1 Tesla magnet is really, really strong. All right. Or a magnetic field that provides, in its core, 1 Tesla of magnetic field strength is really, really strong. And the Earth is only a half a Gauss. And that's at its strongest. So depending where you are on Earth. All right. Well, it's 77 degrees in here. That's nice. But what time is it? 11:06. All right. We'll finish with that. Let me repeat. Can you switch to the document, to the computer? This example here, I think I have on bypass. I don't really like too many of the examples, but go ahead and find one of my. Okay, right at about here, that's kind of what we just did, except they had a sine theta. Theta was equal to 90 like us, so you can review this. This is about as far as we will go and about as fancy as we will go calculation-wise on exam 2. All right. Now, I saw that one of our illustrious learning assistants posted, by my intervention, a study guide. My warning to you is that she knows nothing of my exam, and that's by design, and she's not allowed to. Neither is my illustrious GTA. Therefore, when you're using that study guide that she's provided you, be alert that it's not my study guide and I'm writing the test. My study guide are the notes that you have taken. And hopefully you've taken good notes over the past few weeks. All right, now just to repeat, we will not have electric field calculations. We did all that drill and all that practice, but that's not going to be on this exam, so don't worry about that. But do keep it in mind in case we have to take it on the final and tackle it again on the final. All right? All right, you're dismissed. I'll see you on Wednesday. Do you mind that, Kendra, do you mind that I just gave them that warning?
But I mean,
I didn't look at it, and I'm not going to look at it. And the reason is because, no, but I never look at, when we have supplemental instruction, the SI leader always puts up a study guide, but I never look at it either. And I always make a caveat to the students about that. And I don't want you, you've been a great LA, all right, but it's definitely true that you don't have a mental hypnosis, telepathy with the test writing part of my brain. So,
If they
so you
can
don't know.
if they can do the study guide though, they should be able to do any test that has to do with any of these concepts. I made it pretty hard.
Really? Oh, very. Ooh,
Very,
nice.
very in depth.
Excellent.
Hi.
Hi.
I forgot my clicker. I don't know if you'll even accept that.
No, no,
Okay.
I don't do that. Just gotta bring your clicker.
I know.
Yeah, so, yeah.
So you guys
Yeah, lecture and class, everything that we do in here is primary. If it's not in here, or the couple little homeworks that we had, it's not going to be on the test. And so Kendra might have stuff that's not going to be on the test.
So if it was in the textbook, we didn't cover it.
Kind of, yeah, yeah. Yeah, the textbook is meant to support our sessions, lectures and demonstrations and stuff. Okay, let's get